Hi. In this lecture, we're going to touch upon a pretty interesting, but at the same time quite challenging theme called the magnetic scalar potential. So the discussion begins by observing that away from the current source, where the current density vector will be zero, then the curl of the vector of the magnetic field is also zero. And such condition is easily satisfied if we pretend that this magnetic field is given as the divergence or as the gradient of some scalar function. And if so, then this type of function will automatically satisfy the curl-free condition. And such potential may be called the magnetic scalar potential. And then the equation which is to be satisfied by the magnetic scalar potential will be this second one, namely the divergence of the magnetic field being identically zero leads to the condition that the Laplacian of the magnetic scalar potential be zero everywhere. And this is an absolutely true statement because we know that there can be no magnetic monopoles anywhere in the universe. So, as long as we're able to define the magnetic scalar potential, then this scalar potential also has to satisfy the Laplace equation. And we already have plenty of experience solving Laplace equations in various geometries. So we can certainly bring that expertise into solving some of the problems in magnetostatics. And that's kind of parallel is what we're going to exploit in this lecture. Okay, so such analogy will be exploited in the context of this problem of a current ring whose radius is r, and there's a current I flowing through the circumference of the ring. And of course, we have already seen this problem and solved it to some extent by calculating the magnetic field along the axis of the ring. But certainly, we were not able to calculate the field away from the axis. That problem was a little bit too challenging, and we certainly did not have the tools to solve the situations away from the axis. But using these magnetic scalar potential technique, we might be able to go a step further and calculate the magnetic field strength at locations other than the points on the axis. So that's the kind of theme that we're going to explore from now on. And the Laplace equation in spherical coordinates is what's in order here, because obviously the nature of the problem demands that we think of solving this problem in the spherical coordinates. However, because the source of the magnetic field has a circular shape, it's also obvious that there will be no azimuthal angle dependence in the solution. And so therefore the only two relevant coordinates will be the radial distance r and the polar angle theta. And when we write out the Laplace equation in the polar coordinates and drop the azimuthal angle dependence, we already know what the general solutions look like. And the general solutions are combinations of r to the lth power and r to the minus L1 power, multiplying the angular part of the function described by the Legendre polynomial of order L. Okay, and this is in fact the kind of combination that we saw emerging when we studied the electrostatic potential due to a ring with uniform charge coating the ring. So we can borrow exactly the same math that was worked out in that problem of a charged ring. However, the only difference now, as I will emphasize in a little while, is that this infinite series should begin at L equal to 1 order, not L equal to 0 order. And in fact, this has something to do with the fact that we're dealing with a magnetic problem, not the electrostatic problem. But anyway, in a moment, I will show you why the first term, which might have been there, namely the L equal to 0 term, has to be absent in this particular problem. So for distances less than the radius of the ring, we have this expansion, and for distances larger than the radius of the ring, we have the other expansion. Both are designed to ensure that you don't have a diverging potential anywhere in its respective spaces. Okay, so as usual, now we have to face the task of finding out what the coefficients are. In this case, we're going to exploit the known results. By known results, I mean the answers that we already had for the magnetic field along the z-axis, and the answer was given by this function. And according to our new suggestion to express the magnetic field as the gradient of some magnetic scalar potential, this function should be expressible as in terms of its corresponding magnetic potential. And it's pretty easy to confirm that this is a desired potential form. And one can check this pretty easily. You just act on this scalar function with the gradient. And since this is only a function of the z coordinate, the gradient will only produce the z component. And working out the first derivative of this function immediately gives you the form of the magnetic field we have written down over here. So this must be the desired magnetic scalar potential we are looking for. Okay, so we have found the magnetic scalar function, but only along the z-axis. What we want is quite a bit more than that, because we want to find out what the magnetic scalar potential looks like as a function of both the radial distance r and the angle, right? And what we have here is the expression just along the z-axis, corresponding to the to the polar angle equal to 0. So if I can take the angle theta to be 0 in this general expression, then this expansion must be reduced to the expression I have just worked out over here, this expression right here. But the problem is that this answer is given in a closed form, whereas this series expansion form is given as the series. So one has to find a way to match the series expansion to the closed form like this, which is presumably consequence of summing over such an infinite series. Okay, so here the technique you need is to use the so-called generating function form of the Legendre polynomial. And according to the general theory of special functions, you take such a function and you do the Taylor expansion of this function in terms of t. So given these infinite series in terms of various powers of t, turns out that the relevant coefficients at each order is precisely the Legendre polynomial. Now, on the basis of this general result, we can say that if I expand such a function over here, and this would be the case where x is 0, then the corresponding expansion will give you various powers of z over r plus times the coefficient, which is the Legendre polynomial at the value of x equal to 0. Okay, so therefore this expression that we got as the magnetic scalar potential of the ring along the z-axis allows a series expansion form like this. Okay, or just by redefinition, you can also write it like this. And this expression better match the more general expression I have written out here in the special case where cosine theta is taken to 0. Sorry, cosine theta, since theta is 0, cosine theta is 1. Sorry, yeah. So then, according to such a matching condition, this coefficient whose values we were trying to determine has to be exactly this thing over here. Okay, and therefore we're now able to fix the coefficients and obtain the series expansion of the magnetic potential for arbitrary r and arbitrary angle theta. Okay, but in addition, knowing that the value of the Legendre polynomial when its argument is 0 is also 0 when the order of the polynomial is odd, this sum becomes only the sum over the even. Should be careful. Only over the odd powers of its argument. So just collecting the terms that do survive the summation, I obtain this final expression in this form. Okay, so finally we are able to extend the previous expression for the magnetic field, which was confined to the z-axis, to arbitrary point in space. So what I mean by that is that now that we have these potential, all we have to do is to take the gradient of this potential, which will then give us the magnetic field at arbitrary locations in space. Okay, and when you do that and draw the field lines that you obtain from the analysis, this is the kind of pattern of the magnetic field you will find as generated by a circular ring of the current. Okay, so obviously, this sort of circular ring of current is pretty easy to generate. You just have to wrap a wire in the shape of the ring, and you can even wrap it many times over and strengthen the amount of magnetic field thus generated. So, this sort of ring structure of the current carrying wire has been a popular engineering design for well over a century. And and the way that the strength of the magnetic field falls off as the distance from the plane of the ring is this function. So when you plot that on a graph, it will look like that. It's a fairly slowly decaying function, only as the third power of the distance from the ring. Now, it turns out that someone in the middle of the 19th century noticed an interesting fact about this function, and the interesting feature comes from taking the derivative of this function. So the first derivative, which is easy to work out, is always negative, and that's hardly surprising because the strength of the field obviously vanishes, obviously decays as you move further out from the plane. But what is perhaps less trivial is the fact that when you work out the second derivative, then this second derivative becomes a zero, because at some point it changes sign from being negative value to a positive value. And when that happens, we call that an inflection point. And if you do this algebra, then it turns out that the inflection point occurs when x is exactly 1/2, or when the distance is exactly 1/2 of the radius of the ring. Okay, so revisiting this magnetic field versus the distance z graph, what happens is that when the distance is half of the ring radius, the second derivative of this function vanishes. And that means that in some sense, the magnetic field variation becomes rather slow right around this point of inflection. Okay, and this might be an interesting observation and a useful one for those for those of you interested in the design of magnetic coil and so on, because the ability to generate a magnetic field which is uniform over an extended region in space can certainly find quite a few engineering applications. And the even more interesting observation was made by a great 19th century scientist, Helmholtz, who noticed that who noticed the following. Well, if you can generate a fairly smooth magnetic field with one ring, then what will happen if you add a second ring? So his suggestion was to create an identical coil, both having the same radius r, and you put them in tandem with the separation also equal to the radius of the ring. And ask yourself, what is the magnetic field right down the middle between the two rings? So we already know what the magnetic field is generated by one of the rings. And if you have a second ring, then the magnetic field simply becomes the sum of the fields generated by each ring. And therefore, the total magnetic field will be expressed in this way as the sum of two terms. And now, as we already saw from the previous exercise, one of these terms will have its second derivative equal to 0 when the distance is exactly half of the radius. But this other function that you have just added also has exactly the same feature. And therefore, even this superposition of the magnetic fields will have a second derivative equal to 0 halfway between the rings. But to make the case even more powerful, Helmholtz noted that it's not just the second derivative that vanishes at this midway point, but also the third derivative vanishes. And the vanishing of the third derivative is sort of guaranteed by simply the reflection symmetry of the whole setup. Okay, so right down the middle, this point is halfway between this ring and this other ring. And therefore, the magnetic field function plotted as a coordinates with respect to this midway point has to be an even function, which means that any odd number of derivatives about this point will be 0. So therefore, the first non-zero variation that you find in the vicinity of this midpoint comes from the fourth derivative, which is presumably a very weak effect. So therefore, in this geometry of two identical coils separated at the distance equal to their respective radii, you expect a extremely uniform magnetic field in the vicinity of the midpoint. Okay, so that was the design principle behind what's known as the Helmholtz coil. So the design itself is very simple. You just put together two identical rings and separate them at the distance equal to their ring radius. But such a simple design can give rise to a extremely homogeneous magnetic field. And that's quite useful from engineering perspective. Okay, so the final point of today's lecture is this topological aspect of the magnetic potential. So as I already mentioned, this magnetic potential gives rise to the magnetic field by the operation of the gradient. And that implies that once you perform the line integral of the magnetic field along a certain path in space from point B to point A, then the result will be the difference of the values of the magnetic scalar potential at their respective locations. It simply follows from the principle of integration. But we also know that if we perform this sort of line integral along a closed loop, such as the one shown here, then the result of that integration equals the amount of current that passes through such a loop. That was the Ampere's theorem we discussed last time. And according to this formula, then this current multiplied by some constant equals the difference of the magnetic potentials as it traverses along these closed loop. Now, if this if this magnetic potential was a one valued function of the position, so that at every location in space you only have one possible value assigned to the magnetic scalar potential, then obviously since you start and end at the same place, the difference has to be zero, which then would be incompatible with this other important conclusion of magnetostatics, that the line integral of the magnetic field equals some non-zero value equal to the current passing through it. So the conclusion we can draw from this observation is that this magnetic potential is not a single valued function of the position. It's a multiple valued function. So this is a rather special kind of function that one has to be careful in dealing with. And so there's some sort of topological aspect to this function, in the sense that as long as the closed loop encloses the current, then it doesn't matter what kind of path you choose. The result of the integration will always be equal to the current that passes through the loop, which also equals the difference in the value of the magnetic scalar potential as you follow that closed loop. So, meaning that any smooth deformation of the loop shape does not change the value of the integration. And such kind of phenomenon is usually labeled under the broad idea of topological aspect or topological something. If some result of the calculation does not depend on the smooth deformation of the shape, then you say that the corresponding phenomenon is topological. And also, as long as the loop, no matter what the exact shape, fails to enclose the current, then the result of integration will be zero. And therefore, these difference of the magnetic field potential is also zero, which makes the magnetic field, magnetic potential single valued. So although there's a great deal of analogy between the magnetic potential we have been working with so far, and also the electrostatic potential we worked with earlier, both satisfy the Laplace equation, for example. So despite these mathematical analogies, there's also a huge fundamental difference between the nature of these respective potentials. And this is something I think one better has to keep in mind.